When you hear a flood is on its way, you want answers, right? You want to know what's going to happen. Well, the science behind that prediction has completely changed. Today, we are going to pull back the curtain on how flood forecasts are actually made and how we've moved from making a single perfect-sounding guess to a much smarter, more realistic way of looking at all the possibilities. Let's dive in.
So let's just start with the big one. Why is this so hard? I mean, it sounds simple, doesn't it? A lot of rain falls, the river goes up. But it turns out the journey that a single raindrop takes from the sky to potentially flooding your town is, well, it's packed with chaos and a ton of hidden variables that make a simple prediction almost impossible. This is the kind of forecast we used to get, a single, super confident number. And yeah, it sounds precise, it sounds like something you can rely on, but honestly, it's dangerously simple. This statement completely hides all the uncertainty we just talked about. It gives this false sense of security, and as we're about to see, reality is never, ever this clean.
All right, to really get a handle on the forecast, you have to understand the journey. We've got to start at the beginning, how rain actually turns into the water flowing in a river. This is like the absolute bedrock of hydrology.
Okay, the star of our show here is a little thing called runoff. The easiest way to think about it is it's the leftover water. When rain hits the ground, the landscape is like a giant sponge, just soaking it up. But every sponge has its limit. Once it's totally saturated, any extra water has nowhere to go but to start moving across the surface. That is runoff, and it's what makes a beeline for the nearest river, becoming the key ingredient for a flood.
So let's trace the path of one raindrop. First, it might land on a leaf or a tree branch. We call that interception. It never even hits the ground. If it does make it to the ground, it's going to try to soak in. That's infiltration. And it's only the water that's left over, the stuff that couldn't get soaked up, that becomes our critical runoff and starts heading for the river.
So how do we keep tabs on all this runoff once it's in the river? We use this amazing tool called a hydrograph. And honestly, the best analogy is that it's an EKG for the river. It lets us see the river's pulse, its heartbeat, as a storm moves through. This is probably the single most important chart in all of flood forecasting.
And just like a heartbeat on a monitor, this graph has very distinct parts. You've got the rising limb. That's the pulse quickening as all that runoff rushes in. Then you hit the crest. That's the peak, the absolute moment of maximum flow and maximum danger. After that, the falling limb shows the pulse slowing back down. And the base flow, that's just the river's normal resting heart rate. If you can read this shape, you can understand the flood.
Okay, so we've got the concept of a hydrograph down, but how do we actually, go out in the real world and measure what the river's doing to even create that graph? This brings us to the hands-on, practical side of things, and a really big challenge.
Here is the fundamental problem for every hydrologist. Measuring the water level, what we call stage, that's pretty easy. You can put a sensor in the river and get a constant stream of data. But what we really care about is discharge. That's the actual volume of water moving past a point. And measuring that, it's hard, it can be dangerous, and you just can't do it 24/7. So, we've got the data that's easy to get and the data we desperately need.
So how do we bridge that gap? With this incredibly clever tool called a rating curve. It's basically a magic decoder ring for the river. Hydrologists go out and do the hard, dangerous work of measuring discharge a few times at different water levels. Then they plot those points and create a curve. That curve becomes their translator, letting them take the easy, non-stop water level data and convert it into the super valuable flow data they actually need. It's brilliant.
Now, knowing what's happening is great, but we also have to know where. That's where chainage comes in. Just think of it like an odometer for the river. It's a simple measurement of distance along the river's path, but it lets us be incredibly precise. We can say the flood is going to peak right here at chainage 1500, and that critical bridge we're worried about is at chainage 2200. It's totally essential for mapping everything out.
So now we've got our whole toolkit, right? We've got the hydrograph, the rating curve, the chainage. We should be all set to predict floods perfectly. Well, this is where our story takes a sharp turn, because the real world is infinitely messier than our neat and tidy models.
And this really gets to the heart of the problem. In some perfect, straight, concrete channel you'd see in a lab, our rating curve would work like a charm. But real rivers, they have crazy bends, they have debris, they have all sorts of complex behaviors that can take our beautiful little translator and just break it.
So this is the ideal world, the world our simple tools assume. As the water level goes up, the flow rate goes up in a nice, clean, predictable way. It's a simple one-to-one relationship. It's beautiful, it's easy, and it's rarely true in real life. Now, let's look at what actually happens.
Say hello to the backwater effect. You see, a bridge downstream, or a narrow canyon, or even another river dumping a ton of water in, it can act like a temporary dam. It creates a bottleneck. Water starts to pile up and back up, and all of a sudden the water level upstream is way higher than it should be for that amount of flow. And just like that, our rating curve is useless because that simple relationship between level and flow is gone.
And if that wasn't enough, here's another huge wild card. Tributaries. These are the smaller streams and rivers that feed into the main one, and they are a massive source of uncertainty. And it all comes down to timing. Imagine if the flood peak from 2 or 3 of these tributaries hits the main river at the exact same time as its own peak. You get this catastrophic pileup, a combined event that is way, way worse than any of them would have been on their own.
So we have rain we can't perfectly predict, a messy river that breaks our rules, and all this crazy timing to worry about. How in the world can we make a forecast that's actually reliable? Well, this brings us to the modern solution, a way of thinking that actually embraces all that uncertainty instead of trying to pretend it doesn't exist.
Let's go all the way back to that first flawed forecast. This single number, this deterministic prediction, as they call it, it pretends to know the one true future with absolute certainty. But now that we've seen all the chaos involved, we know that's just not possible. It ignores every single complication we just talked about.
Now, check this out. This is the modern forecast. Instead of one number, we get a whole spectrum of what could happen. And this is the key part. Each one has a probability attached to it. This doesn't tell us what will happen, it shows us what could happen. Sure, there's a 30% chance the peak is around 5.1 meters, but look, there's also a 10% chance of a much more serious flood hitting 6.5 meters. This is an honest, complete picture of the potential future.
So how do they do this? The technique has a cool name, ensemble forecasting. Think of it this way. Instead of placing one single bet on what the future holds, forecasters place hundreds of bets. They run their powerful computer models over and over again. Each time, they just slightly tweak the starting conditions. A little more rain over here, maybe the ground is a little wetter to start with over there. Each of these runs gives a slightly different but totally plausible outcome. And when you look at all of them together, you don't get a single prediction, you get a map of what's possible.
This quote from the research really just nails the entire idea. It sums up the whole philosophical shift. We've stopped chasing the impossible dream of a single, certain answer. Instead, we're now trying to understand the full range of what could happen and what the chances are for each one. That's the heart of modern forecasting.
So why is this such a big deal? Well, because it allows people to make truly risk-based decisions. An emergency manager isn't just looking at one number anymore. They're seeing the actual probability of a really bad flood, and that lets them weigh the costs and benefits of big decisions, like ordering an evacuation or closing a major highway, way more effectively. It gives them the whole story.
And that brings us right to the final question, and it's really for you to think about. It's one thing to be told, hey, a flood is coming. It's a totally different thing to be told there is a 30% chance of a major destructive flood. What would you do with that information? Would you move your car to higher ground? Maybe start packing a bag just in case? It's that power, the ability to act on probability instead of false certainty, that shows the real value of modern flood forecasting.